All right, welcome back. Hope we all had a good weekend. Welcome back to the normal schedule. I know a lot of y'all still need to watch last lecture. When I looked last night, I only seen 2 views on YouTube. So that kind of worries me about people understanding what we're going to be diving into today, since it's going to be a continued event of last class. So please remember to stay up with these lectures, watch them ultimately, and try to watch the rest on time, yada, yada, yada. But our due dates are up here. The 16th has already passed, obviously, so we can delete those. So 4.5 is due on the 23rd. 4.6, I believe, will finish today, so that should be due on the 28th. Our test 3 and final exam are going to kind of come back to back. Test 3, I really wanted to put this section on it, 4.6. But I don't like testing on something without having a week of that information available, pretty much excluding the final. I make exceptions for that every now and then, so I'm going to keep 4.6 off of it. But it will be on the final. Please understand that 4.6 will most definitely be on the final exam. I will absolutely make sure to have one of those problems on the final exam to make sure that you've been tested on it. So 5 sections from chapter 4, arguably only 4, because 4.3 we really just covered as a concept, not as, hey, do all the homework and do these 50 or 100 different little rectangles and stuff. Now, I can still ask you a question on the concept of 4.32. I think I have that section number wrong. Yeah, I do. It's 4.2. What I said 4.2, but I typed 4.3. So again, no official like real math problems in 4.2, but the concept is still important. I can still test on a concept if I really want to, but you know I'm not that into it. So that's going to run the 24th to the 27th, which should be Friday through Monday. So Friday, Saturday, Sunday, Monday. You'll get 2 attempts just like the first 2. I'll provide a review to you by Wednesday. I am slam booked today, so I'm not going to be able to work on that as soon as I end class, blah, 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 blah. I can't do it today, but I will provide it Wednesday by 5 p.m. Final exam. Now, this is going to run different than the first 3 tests. It will be Thursday, July 30th of this year, obviously. It is one and only one day. We will not hold regular class due to the final exam. So most people don't do a class on the final exam day. How are you going to test on something you just went over that hour, right? It would just be silly. Also, because I'm only giving this test on one day, some of you may need the class time to take the test. So it's only going to be one attempt. I cannot give multiple attempts to a final exam. I just can't. Probably shouldn't even allow it for the regular test. And the thing is, almost nobody takes the 2 attempts anyway. So probably going to be something that you might be the last class to get that option moving forward with this format. Probably going to be the last class to do it. But when this whole issue started up, I wanted to be as fair as possible with changing situations, but we should be getting a little more used to it. People that sign up for classes in the fall, blah, 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 stuff you don't need to hear about. Sorry, I'm ranting. So for the final exam for the review, well, you got a review for tests 1 through 3. I'm not really going to throw curveballs from those chapters on the final exam. So guess what? You can just go back to the previous 3 reviews that will be covered up to 4.5. And then I'll give you I will give you an extra review document or assignment, but it's not going to cover anything from chapters 1 up to and including 4.5. It's going to include 4.6, I think 5.3 and 6.1. I believe those are the next 2 sections that we'll be able to cover. If I have time to, again, go over an extra few things, we will, but we really only have 3 more classes together. It's today, this Thursday, and the next Tuesday, because the following Thursday is final exam day, and like I said, we won't hold class on a final exam day. So yeah, those few extra problems will be provided soon. I'm not going to hammer out a date. You'll get it no later than the 28th. I might have it ready by the 27th, but it might be ready the 28th. And again, it's not going to be a big set of examples. It's only going to cover 3 sections roughly, maybe 4 if we get further than I anticipate. Okay, So you know, and this is obviously not the 21st. I think I changed that. Oh, I know what happened. I had to let my dogs out and put them back up. That's what it was. And I got distracted. Okay. So I will very quickly, quote quickly, kind of scroll through and discuss what we talked about last time in 4.6, integration by parts. So 4.5 is where we start these more advanced integration techniques. 4.5 was integration by substitution. And again, to reiterate that process, which will be tested on test 3, you have to say let u, or whatever letter you like, equal something. And we generally let that be the inside of a what look like a composite function or a natural log, if there's a natural log somewhere, a denominator, or the inside of a denominator, something like that. Then we took its derivative, and we had a very specific process. We solved it for dx, and then we plugged u and dx into the original integral, and then we hoped that all of the original variable would disappear, and that we'd only have something like the integral of u cubed du. There couldn't be a dx anywhere because we replaced it. There can't be any x's, they have to cancel. We might end up with an extra constant somewhere, usually in the bottom, but it gave us a much prettier integral that we could do with our one of 4, 5, or 6 basic rules. We have the power rule, we have the constant rule, which is just an extension of the power rule. We have the natural base e exponential rule and its variation, which is kind of like chaining. And then we had the natural log rule, the absolute value of natural log when you integrate 1 over x. But then after you integrate, you had to go back to the original variable, because if I give you a problem in dollars, I want the answer in dollars. We also saw some examples with upper and lower limits when we had to do a definite integral, and we said that one method, the suggested method, was to convert the endpoints to u values as well. So if in x you have 0 and 1, that might be the same thing as 1 and 2 for u. And that was literally an example we saw in 4.5. We also said that you could skip that with a little bit of hand waving, and then just when we actually did the evaluations, make sure we go back to x's. But if you want to stay in u's, you have to convert to the values to u values so you can actually plug them in. So if any of that sounds confusing or like you've never seen it before, that means you need to go back and watch more 4.5. So integration by substitution is used when you have a product or a quotient or a chain rule and you think that a substitution would make it look cleaner. But sometimes, and quite honestly most of the time in the real world, there's no convenient substitution. Those substitutions are all hinging on being able to cancel out another pair of x's by taking the derivative of your u and having it be like be a variation of the other part of x's that are there. So like you might have in parentheses x squared plus 3, and then that's raised to the 5th, and then to the side there's a 2x. By letting u be the x squared plus 3, its differential dx would be able to cancel the 2x to the side when you solve for it. It doesn't happen usually in the real world, though. We got lots of problems that are cookie cutter and fit it. But sometimes what you have to do is take more of a general approach, and it's this integration by parts technique. So now we're getting into what you see on the screen. So this technique is used when it looks like a product or quotient or a chain rule, but the substitution technique doesn't actually work. So it's sometimes used, but sometimes it's used for simple looking integrations that don't follow previous formulas. And we will get into that later. But again, this technique is used when it looks like a product or quotient or chain rule, generally speaking. It's used when a substitution technique is usually used. But the way I kind of process things is I look at a problem and the first thing I say is, will the substitution method work? And if I see that when I get that differential part, if it's not going to cancel with everything else that's there, then I go, nope, I probably need to use integration by parts. There are times when both techniques can solve a problem, can integrate, but usually it's a one or the other type of situation. And again, I would generally try the regular substitution first, then integrating by parts. And to take that even further, what I do is if I'm looking at a bunch of polynomial terms, if my inside part has an x cubed and my outside part doesn't have an x squared, that means the substitution is going to fail because that differential bit won't cancel. That is when I go, I probably need to integrate by parts. So we did the proof last time. I'm not going to discuss the proof again. You can see that in last class's lecture, but the general idea was you take the product rule for derivatives and you integrate it, and then you solve for one of the things on the right-hand side. And after you do all the stuff that you do in the solving process, you end up getting this formula. And there are actually two versions of this formula. It's whether you solve for this integral or this integral, but traditionally mathematicians always solve for the u dv. Again, you don't have to. You could say the integral of v du is uv minus the integral of u dv. It just changes what you might want to call your u and your dv, or your v and your du. But this is still a substitution technique. It gives us a formula. And the two things that we have to kind of use this to set up and say, let this be this and let that be that, is we have to say let u equal something and let dv equal something. So in that process, when you say let u be this and let dv be that, you have to take the derivative of the u and you have to integrate what you call the dv. Again, all that is seen here. And then at some point, I made a blanket statement. Generally speaking, u, again, generally speaking, is the simpler looking part. And the reason for this is you're going to end up taking its derivative, and you want the derivative to be even simpler than what you originally started with. The v, the dv part, it just ends up being the rest, and you integrate it. And what you're hoping is the formula on the right side, it's got a v and a du. So du should become simpler, and then v is just whatever it is. You hope that by doing that, that this integral is completable because the original one was not. This technique is known as integration by parts because you only actually integrated a part at a time. One of those parts, you don't even feel like you're doing it naturally, but it does come up, and the other part is direct. Some people say it's called integration by parts because this part is automatically integrated. Yeah, but it's not really automatic. You do it in the process. You have to memorize this formula. This will be on the final exam. You have to have this formula memorized. This will be on the final. It won't be on test 3, but it'll be on the final. Hold on a second. Sorry, I had to cough. So again, your two substitutions, you'll say let u equal blah, blah, blah. You'll let dv equal blah, blah, blah. Generally for this technique, u is the simpler part, which is ironic because in the other technique, we tend to let u be the more complicated part, or at least the inside of the more complicated part. So that's a bigger difference here. And again, I'm saying generally, there's exceptions to any rule, especially when you go to try and integrate a natural log of x, which I point out down here. If there's ever a natural log of x involved, in fact, just like the substitution technique, u is going to tend to be the natural log of x. Again, typically, I could give a problem where it's not, but that's usually the first thing you try. Notice I say try. You're going to try some of these, and you're going to mess them up poorly. You're going to make the wrong let statement. You're going to make an incident somewhere else. But assuming the rest of your math is good, if you make the wrong let statement and you notice that you can't integrate that bit at the end, then you go back and make a different let statement. Now, what's really fun with this type of problem that we won't get into is you can actually do this multiple times. If this integral that you get over here, if this one you can't complete, maybe it's a little nicer than the first one. So maybe you do another integration by parts on this, and maybe you get a simpler integral. I've had integrals where you had to do this 17, 18 times to finally get down to one that you can literally integrate without doing the parts. That won't be seen in here. I'm just saying they exist. When you talk about trigonometric integration by parts, things with sines and cosines, again, stuff we don't do in here, it's actually a really interesting problem because you do it twice and then you have to rearrange and solve for some stuff. But don't focus on what I just said. Memorize this formula. U dv equals uv minus integral v du. And I think I forgot to say integral there. All right, so again, this was a proof, nothing you'd see on a test, but I still think you should check it out. Don't forget to watch the video. Two substitutions. Generally, we use this when substitution fails. Now, when I say fails, maybe you recognize that it's going to fail. You don't actually try it, because I've got plenty of those problems. I'll go, oh, no, these are both polynomial bits, and they're not off by 1 degree, so substitution would fail. Let me try parts instead. So again, here's your formula. I'll write it again later. And we did an example. So the integral of x times e to the x. This is a variation of that x times e to the x squared, which we did by substitution. And I even mentioned when we did that problem, either one or two variations that are simpler looking that we couldn't do. We can't integrate e to the x squared. We can't integrate that way. We can't integrate x e to the x that way. So if you tried to do substitution, you'd probably set let u be x, its derivative would be 1, and when you plug in the dx, this x over here won't cancel, you'll have a mixture of variables, and we can't integrate mixtures of variables that way, for now. There are integration techniques of multiple variables. We don't do that in this course. At least we won't have time for it in this course. I wish we did. So here are the two statements we said. We said, let u equal x, because out of these two bits, x and e to the x, that's the simpler bit. I believe I may have shown you the incorrect way to do it as well. If you did it the other way, how things wouldn't work out. I can't remember now. It's been a week. So we let u be the simpler bit, which is the x, and then dv is the rest, the e to the x and the dx. Don't forget this part. The u, so again, this is the two things we let. We take the derivative of the left side, and we have to use it the differential version. You can't do u prime, because then you won't be able to do this setup. So the derivative of u is du dx, the derivative of x is 1. And then we just multiply both sides by dx, and we get du equals dx. Now this is a little different from integration by substitution. Substitution, we were supposed to solve for dx. This we're supposed to solve for du. If you see these four statements, take the derivative of u and solve it for du. So that's just a little different. Now this one happens to be solved for dx because of the very simple derivative, but that's just a coincidence. So again, substitution you solve for dx, integration by parts we solve for du. The reason we solve for du is because du is in the formula. All right, so we got du equals dx. We let dv equals e to the x dx. We integrate both sides. We show the integration. Integrating dv gives us v because there's a 1 here. So the integral of 1 is the variable, but because it says dv, our variable is v. The integral of e to the x is e to the x. So now we have everything we need. In the formula, uv minus v du, here's the x is the u, so I'll write it. I really need to move that pen before I accidentally use it. So here is the u, which was right there. The e to the x is the v. Then minus the integral, so that's part of the formula, minus integral. V du, the v, we came up with e to the x, the v gets replaced in twice, and then the du was right here, du equals dx. This is du. Those are the four things we replaced. U, v, minus integral, v du. The u and the v, this part doesn't have an integral, it's already done. So this x e to the x stays x e to the x. Here's our minus symbol, here's our minus symbol. Integrating e to the x gives us e to the x, and then we can't forget our plus c at the very end. Okay. So how did we use this once again? We let u be the simpler looking part, generally. dv is the rest. Integrate the dv to get v, take the derivative of u and solve it for du. Again, special memo, which we will see an example of, I promise. If a natural log is ever involved, you're generally going to let u be the natural log. Now, 20 minutes in, we'll finally talk about a new example. So that was example 1a. We'll call this b. Let's do the integral of x cubed times the natural log of x dx. So if you try to do substitution, there's a natural log, so you'd set let u be the natural log of x. Its derivative would be 1 over x. Then when you solve that for dx, you would get du over x. And then when you plug that in, you would have an x in the bottom and you'd lose one of the x's here, so this x cubed would go down to an x squared, but now you'd have an x squared here and a u here, and that will fail because you can't have mixed variables and integrate this way. So substitution technique would fail here, as just verbally described. So we got to step it up to this integration by parts. And again, that formula is the integral of u dv equals uv minus the integral of v du. Third time I put it on the screen because it's so important. So we'll say let u equal the simpler part. Now, generally you'd say x cubed is simpler, but I made that little special 3 asterisk memo. If natural log is involved, let u be that. So just trust your teacher and try it out. Let's see if it works. Which makes dv the rest. So this right here was the u, and let me switch colors. So dv has to be everything else besides the integral symbol, so the x cubed and the dx. We take the derivative of the u, we integrate the dv. So du dx, the derivative of the natural log of x is 1 over x. That's a formula you should still have memorized. You never get to forget any formula from this class ever. Sorry to say. And then we want to solve this thing for du. Again, this is the slight variation of the substitution technique. We're going to solve this for du, not dx. So I just got to multiply both sides by dx. Oh, that is awful. Let's not do that. So dx on the left, dx on the right, so that those will cancel. And you end up with du equals dx over x. And actually, I said something wrong earlier. I said that the x cubed would cancel. If you solve that for dx, the x goes on that side and actually stacks up to an x to the 4th. It gets worse. Sorry about that. Either way, the point was it did work. So now what we get is du equals dx over x. If you want to leave that as 1 over x times dx, you can. I'm just compressing it. So the dv, we're going to integrate. Whatever you do to one side, do to the other. We like these separated because there's no funny business. There's no mixture of variables. This is actually called separation of variables. It's a fancier name for a fancier technique, but this is just a lower version of it. Integrating 1 just gives you that variable, so that's a v. Integrating x cubed gives you x to the 4th over 4. So those are the things we need. We need the du, we need the v, and we also need the u. Those are the 3 things that get plugged in. We don't actually plug in dv. dv was just necessary to get to where we're going. It's 3 of these 4 that get plugged in. So what we now get, the integral of x cubed times the natural log of x dx, which we're now calling the integral of u dv. This is now equal to u times v. The u is the natural log of x times v. V was x to the 4th over 4. I'm using color this time to at least show if it came from a u or a v. So again, that was uv. Then we have a minus, and an integral. And this will be v du. So we're going to use the v again. So there's an x to the 4th. I'm sorry, that should be blue. X to the 4th over 4. So that's the v. And then times the du. Du was dx over x. So let's clean this up some. First of all, the natural log of x times x to the 4th is not the natural log of x to the 5th, because this x counts as inside, the x to the 4th outside. It's actually better to write the x to the 4th first. So all in one color now, that's x to the 4th times the natural log of x all over 4 minus integral. I'm going to bring this 4 out front, so that's a 1/4, then my integral. Again, this 4 in the bottom is now just out front of it because it won't have any effect. And then we add 4 x's in the top, 1 in the bottom. You lose one of them, so we got x cubed dx. So this first bit has already been integrated. There's no integration symbol there. Do not integrate it. You can't integrate it. In fact, it is worse than the original problem. But that's okay because we don't need to mess with it. But what we can integrate is this bit right here, and it's an extremely simple power rule, which the original problem was not. That's what parts does for us. It gets this kind of ugly bit out of the way, which we take with a leap of faith. I mean, again, we prove the formula, so it's not really a leap of faith, but if you don't follow the proof, then you might feel like a leap of faith. But it is just, it takes the product rule of derivatives and integrates it and rearranges it is all it is. You might say, well, why didn't do the quotient rule? Maybe there's a method out there that involves that. Maybe you're glad we don't use it. Okay, so integrating x to the third, well, we literally already did that earlier, and that's what's also funny, integration by parts. Very often you get 2 of the same integration, so you should really know that. All right, so x to the 4th, natural log of x all over 4, minus, here's our 1/4. Integrating x cubed gives us x to the 4th over 4. That's times. And then we integrated, so here's our plus c. 4 times 4 is 16. So this would be x to the 4th, natural log of x over 4, minus x to the 4th over 16 plus c. That is one way of writing it. If you prefer to have the fractions out front, you can always do that. So 1/4 times x to the 4th, natural log of x, minus 1/16 times x to the 4th plus c. Same answer. Neither I nor my math lab care which way you did that. This is the most involved integration technique that we get. I can guarantee that. But it's a good technique. It's a very important technique because in the real world, most integrals are not so clean or clear-cut and dry. I've seen way more problems that look like this in the real world doing actual math, not just from a textbook, versus just integrating x cubed. I'm not saying I haven't seen plenty of these x cubed. I'm saying I've seen a lot more things that look like this. Because in real world dynamics, things are much more complicated. So that was an example where we let u be, which you might not say is the simpler part, but it's got that special case. Now, what if you tried to do that the other way? What if you would try to do this? And let's pick a terrible color. I like red for wrong, but I use red so much I can't really do this. So what if, I'm going to do this kind of small. Oh, sorry about that. I hope that wasn't too loud. I tried to reach for the mute button in time, but I failed. All right, so here's our original integral, the x cubed natural log of x. What if you did this the other way? So what if you said, let u be the x cubed, and you said, let dv be everything else, which would be the natural log of x dx. Now, this is not a typical substitution. Well, I don't want to say that. You might say, well, just let u be the x, not the x cubed, because back in the substitution technique, you usually let u be the inside. Well, this time the inside isn't like a sum or difference of a bunch of terms with a bunch of different exponents. It's just x. So that's why I don't just say let u be x. It would literally do nothing for us. So we try x cubed. Again, we're used to seeing problems where it was like 5x squared minus 17x plus 3 raised to the 5th power, and then u would be the thing inside the parentheses. This is a very different problem. Okay, so take the derivative. Du dx is 3x squared. All right, integrate. Integral dv equals integral natural log of x dx. Well, the integral dv is v, and the integral of natural log of x is, well, we haven't given a formula for that. We know that the integral of 1 over x is the natural log of the absolute value of x. But that says nothing about the integral of a natural log of x. Question mark, question mark, question mark, question mark, question mark for now. Now, I'm not saying you can't do this, and in fact, it's literally going to be the next example. But for now, we have been led to an integration that we're questioning and we're not sure of. And I would probably just want this to be its own problem. So that's why I'm trying to demonstrate here that this would be not a great path. And that is the main reason why we generally, when we have a natural log of x, we want that to be the u, because you'll take a derivative of it, and we know the derivative of the natural log super easy, but the integral of natural log, while we can do it, it is a little complicated. So that's why I said not a great path, and it's not a good path at all, but I'm not saying it can't be done, it's just not a good path. All right, C. The integral of the natural log of x dx. So again, I just demonstrated why it's not a great idea to let the dv have a natural log of x. So that gives us a clue here. We probably shouldn't let dv be all of this. So substitution is going to fail. If you let u be natural log of x, the derivative is 1 over x, that x is not going to be able to cancel with anything because there aren't any x's to cancel. So you would actually make this worse by using the substitution technique. You'd get the integral of what, x times u. No idea how to do that. So don't do it that way. Let's try out this other technique. Let's say let u equal something and then let dv be the rest. We've already seen that letting dv be the natural log is a bad idea. So let's try letting u be the natural log of x and dv be everything else, which is literally just dx. Again, calculus can be about trying something and failing miserably, trying something again, and then maybe getting it right, maybe third time, maybe fourth try. But you can't expect in calculus to do everything right the first try, at least as you're doing more expansive problems. All right, derivative of the left side. Now I was supposed to do that right in blue. Not a huge deal. So we said let u equal the natural log of x. We said let dv equal dx. Let me just go ahead and integrate the right side so I don't have to keep switching colors. Integrating a differential just gives you the variable. Again, we're really integrating 1, which the integral of 1 is x or v, or whatever letter we're talking about. The left side there's a v, so it's v. The right side there's an x, so it's an x. For the derivative, you get du over dx equals 1 over x. Solve for du, so we multiply both sides by dx, and we get du equals dx over x. It's literally the same as last time, so I'm not going to show the multiplication this time. Now again, we're only going to need 3 of the 4 parts here. We're only going to actually end up needing the du, because that's in the formula. Hold on, give me 10 seconds. Sorry, guys. Okay, so we need the du, we need the v, and we need the u, because the formula has u, v, minus integral of v du. The right side of the formula doesn't have dv anywhere. The dv was just to get rid of the dx, integrate it to get the v. So those are the 3 things we need. So our integral becomes the integral of natural log of x dx becomes integral of, and I'll do my colors perfect this time. So then, why did I write integral? That was the uv. So we, v du. So we have our uv first. The u is the natural log of x times the v is that other x, and again, these will not multiply to make an x squared, minus the integral of v du. So uv minus integral v du. V is the x, then the du was the dx over x. And again, the whole goal of this thing is that this integral ends up simple, one that we know how to compute. And what's cool is it does. So that's x times the natural log of x. I'm just taking the blue one and putting it in front of the red ink. That's all I've done there. Minus the integral of, the x's cancel, That's just the integral of dx. There's a 1 there implied. This is very simple. This is literally the simplest integral you ever get. So that's x times the natural log x times the natural log of x minus the integral of dx is x. Don't stop there though. Don't forget your c. So what is the integral of the natural log of x? It's x times ln of x minus x. Now, if you were in an advanced calculus class, I have seen this on formula sheets, but you still have to memorize. I don't want to say a formula sheet. I've seen this on integration sheets, but students are expected to memorize those. Regular calculus students have to memorize 20 or 30 of these things, just like they have to memorize 20 or 30 different derivatives. We only have 4, 5, 6 each. We have a much easier job. Sorry, I had to go turn something off. This is not one we expect you to memorize because it's a little wackier. The integral of natural log of x is x natural log of x, then minus x. It's kind of an interesting formula. You can call it a formula and you can memorize that. If you can memorize that, if I gave you this as a test question, you could certainly use that formula. But what I expect my students to do, since I don't say it's a formula, I don't put it on a formula sheet, I expect them to do integration by parts to get this. Now again, if you chose to memorize it, that is your decision. And at one point in my life, I had this memorized. I will admit I don't have it memorized off the top of my head right now, because I just do it by parts. I can do it in about 20 seconds. That's because I've done it a lot. So it's kind of funny. You would never think that this problem, because it's only got one term in it, one bit, you would never think integration by parts would work, because integration by parts is usually used for things that look like products or quotients or chains. This doesn't look like any of them, and yet it works. There are other there are other classifications of functions where this works. And it's not polynomials. So what you could say, all right, we'll go back to the green. Now that we know how to integrate natural log of x, that makes the v this thing. X ln of x minus x plus c, which is kind of ugly. And if you go and plug that into the formula, so this would be minus the integral of v du, back up here. So the v is this thing down here. The du is this 3x squared. Do you know how to integrate this black ink times this green ink? Again, going back up here. What you could now say is that this is equal to the original integral is equal to uv, which would be x cubed times x ln of x minus x, ignore the plus c when you're doing that, and then minus the integral of v du. So du is 3x squared, so that's going to be x ln of x minus x times 3x squared dx. What in the world has happened here? That looks atrocious. Now, here is what's interesting. You can integrate it. That is integratable. Because look at this. We did x cubed natural log of x in example B. It required parts. When you distribute this, this term right here is going to end up being 3x cubed natural log of x. So it's just the same answer, but with a 3 in front of it. This last part would be integrating 3x cubed, but again, it's terrible. You already did integration by parts to get to v. Now you're going to have to do it again, as well as there's a lot more to integrate. There's 2 bits to integrate instead of just 1. That's why I didn't say this is wrong. I said it's not a great path. Okay. All right, so not a great path aside. Let's work on the ones that are. Let's do some more. I like lots of practice with this stuff. So let's do about 2 more like this, and then we'll get to one with endpoints, with upper and lower bounds, an area, if you will. So the integral of x plus 1 over e to the x dx. So if you tried the regular old substitution One student might say, let u be e to the x, and then when you solve for its differential dx, it's definitely not going to cancel the x plus 1. Another student might say, well, just let u be the exponent. And if u is x, its derivative is 1, and it won't cancel this x plus 1 when you go through and plug in the differential. Substitution fails miserably on this problem. Parts is the way to go. So we say, let u be the simpler part. What do you think simpler, x plus 1 or e to the x? I think x plus 1 is simpler. Polynomials are simpler than anything else. Exponentials, radicals, rationals, etc. When you take its derivative, the derivative of x is 1, the derivative of 1 is nothing. When you solve for du, I gotta sneeze again. I got it that time. Muted in time. All right, multiply both sides by dx, you get du equals dx. Again, it's kind of funny because substitution technique, you solve for dx. Integration by parts technique, you solve for du. These are both solved for the same thing. That's because of the very simple derivative. This can happen. Does it happen a lot? No. Does it happen frequently? Actually, yes. Maybe 20% of the time, 25% of the time. So there's the u branch. Now let's say let dv be the rest, which the e to the x is in the bottom. Be careful there. So dv is actually dx over e to the x. And then when you go to integrate it, oh, that looks terrible. That looks like ex, e to the x. There you go. So that'd be the integral of dx over e to the x, which it's just going to be better to write this as the integral of dv equals the integral of e to the negative x dx. We don't know how to integrate when an e is in the bottom, but we do when it's in the top. So there's that classic give it a negative exponent to bring it up. So integrating dv gives us v equals. The integral of an e to the x is itself, but we did have that special case of the formula where if there was a coefficient here, you had to divide by that coefficient. So this is e to the negative x itself divided by the derivative of the, I'm sorry, not the derivative, I don't want to say it that way, the coefficient of the exponent, -1, which is just negative e to the negative x. I need a minute to blow my nose and cough. Must have kicked up some dust particles. Okay, so since I kind of wrote that weird, let me just write it all together here. V is negative e to the negative x. And you might say, well, why don't you bring that to the bottom? Because I'm going to ultimately integrate that. So I'll write it both ways, or v equals -1 over e to the x. You'll see it both ways ultimately. All right, so going back to the original problem, the integral of x plus 1 over e to the x dx becomes, and again, I'm not plugging things into this, I'm plugging them into that formula. And one more time as a reminder, the integral of v du is uv minus integral v du. There's a lot of bounciness to our calculus formulas. It's kind of going back and forth. V du, v du, I said the same thing twice, didn't I? That's udv on the left. I just always have the right version stuck in my head. It's the integral of u dv, because that's based on, we said u and dv. So u dv is uv minus v du. There's this bounciness. If one of the sides is u dv, the other is v du. The term that's already integrated is the u and the v. No differentials, and it's got a minus to it. All right, and the bounciness of it is because it was derived from the product rule. All right, so integral of x plus 1 over e dx dx. U times v. U is the x plus 1 times the v, which is the negative e to the negative x to the negative 1 over e to the x. Now, I'm going to have to wrap this first bit in parentheses because of that. Probably going to need the second bit in parentheses as well because it's a negative. So negative e. I'm not sure which to use yet, or the students might not be sure which to use yet, so I'm going to use the original negative e to the negative x. Now, I'm not going to integrate this, so spoilers, I will switch it to this one very soon. Minus integral, then v du. So the integral does not have either of the original bits. It doesn't have the u and it doesn't have the dv. It's got the v and the du, the bottom. So the original integral parts that we use to determine the substitution, neither of those should be in that last integral. That's another way that might help you memorize things. This bit should always be the last bit from each of these. So v and du. The v was the negative e to the negative x. Oops, wrong color. And then the du was just dx. It's really nice when the differentials are the same exactly. That happens when your u is just a linear x and maybe a constant with no coefficient here. If this was a 3x, there'd be a 3 there. It would just change it a little. Let's clean this up some. The negative, let me write out front. The x plus 1, whether you write that in the front or back is up to you. But I kind of like to write it in the back because, well, there we go. My e to the negative x, I'll fix up soon. Here's the x plus 1. Again, all I've done is just swap the order of these two things because it feels better to write the monomial part first. Then minus the integral. Well, that's a minus and that's a minus. Those two cancel, so you just get a plus integral e to the negative x dx. Okay, so this is going to become, this has already been integrated, so let me bring that to the bottom. So negative parentheses x plus 1 over e to the positive x. Then plus the integral of e to the negative x is just that thing, e to the negative x, but then divide by the coefficient of the top. So plus e to the negative x over negative 1. And then we do a plus c here. And I did something intentional, and that was that I have this in the bottom now and this in the top. You might not recognize these, there's some like terms going on here. Let's bring everything to the bottom now. This negative, let's bring that to the top, so we'll make that a minus. Again, this minus I'm just going to bring out here. The e to the negative x I'm going to bring to the bottom, make it a positive x. So this is negative parentheses x plus 1 over e to the x plus, minus 1 over e to the positive x. So again, the negative 1 in the bottom made the coefficient negative. The negative 1 in the exponent is why the e to the x is down the bottom and has a positive exponent. Then our plus c. Now, believe it or not, there are like terms here. As this is set up, nothing combines, but if you were to split apart this top fraction, you'd have, ignoring the sign, an x over e to the x and a 1 over e to the x. 1 over e to the x is the same as 1 over e to the x. So we need to separate this or split the fraction, then combine like terms. This is not an acceptable final answer. So that's negative x over e to the x minus 1 over e to the x. That was me distributing the negative to these two terms. The e to the x was in the bottom of the combined thing, so it should be in the bottom of them separated. First term, second term. Then this one right here is what was originally there, the 1 over e to the x. So this third one I just wrote is what was originally the second bit. And then you'll have your plus c after it. Now this term and this term, the second and the third terms are literally the same thing. This is like negative a minus a, 1 over e to the x, 1 over e to the x. We combine those. Negative 1 minus 1 is negative 2. So what we ultimately end up with is negative x over e to the x minus 2 over e to the x plus c. Some people might recombine these and say, oh, well, they both have a factor of e to the x in the bottom. So we could do negative parentheses x plus 2 over e to the x plus c, or negative x minus 2 over e to the x, again, plus c. Oop, I don't want to do that. Let me give it a little more room because that was bad. Negative parentheses x plus 2 over e to the x, then the plus c. Or you could say negative x over e, minus 2 over e to the x, and then your plus c. All three of those are the same answer. All three should be acceptable, but you have to be able to recognize that. Some people might combine like terms while there's still e to the negative x's. That is an option. This is not the only way to have completed this problem. It is very rare that I give you an only way to complete a problem because that's how calculus works. They're usually just the best ways, the easiest ways, so to say. Okay, let's do one more like this. So that was D. And I'm going to run out of room, so let me just put it here, E. This is a longer one. Yeah, I know what you're thinking. Longer than those. Oh, you're going to hate me in a minute. The integral of x plus 2 times x plus 4 raised to the 5th power dx. Man, oh man, you are not going to like me now. So if you try regular old substitution, well, first of all, you got two kind of inside bits. That's a bad sign. Not a sign that it fails. But if you say let u be the inside of the complicated bit, that's x plus 4, the derivative is just 1, that's not going to cancel the x plus 2. Substitution is going to fail. I leave that up to you to try out. Try doing it wrong. Trust me. It will be good for you to see how it fails. So we're going to our substitution technique. Now we've been saying to let u be the simpler bit and dv be the rest. What do you think is, now again, a traditional substitution technique, I'd be attacking the x plus 4 because it's the inside of the complicated bit. This integration by parts, it's usually just separated into a part A, part B kind of thing. So x plus 2 versus x plus 4 to the 5th. Which one looks simpler? Because that's what we should let u be. I'd say x plus 2 looks simpler than something that would be like a chain rule as a derivative. Also, that's a spoiler for later. So we're going to say let u be x plus 2, and then dv will be the rest of it, which I'll write in a minute. We're going to take the derivative. This is going to be very similar to last time. Du over dx equals 1. The derivative of x is 1. The derivative of 2 is nothing. Multiply both sides by dx, and you get that du is equal to dx. So we'll let dv be the rest, which was the parentheses x plus 4 to the 5th power dx. And then we're going to integrate that. So the integral of dv equals the integral of x plus 4 raised to the 5th power times dx. Give me a minute. Sorry, family stuff. Okay. So we integrate. Okay, well, the integral of dv is v. The integral of x plus 4 to the 5th, that's why I was going, well, that's not a straight up polynomial rule. You could take this x plus 4 and multiply it by itself 5 times and spend 15, 20, 30 minutes of your life wasted, wasting time on that. But it works. It's just a matter of, I'm gonna have to mute in another 20 or 30 seconds again, just FYI, maybe sooner. Yep, sooner. All right, so when you look at this integral, it's not a straight up power rule. It's not an exponential rule. It's not a logarithm rule. It's not any of those normal basic rules. It's not a constant rule. So that means we need one of the more advanced techniques. So, well, substitution is supposed to be the first thing that we try out of substitution versus parts, so we try substitution. So that's why I said this problem was going to be a really long one. You've got integration by parts as the core of the example, but then inside of it, you've also got to integrate with a substitution. So ... you have to use a substitution to figure that part out. So let's go to the side and do that as its own problem. So to find v, we got the integral of x plus 4 raised to the 5th dx. We would want to say let u equal, so we're back to the substitution technique, so that's the inside bit generally, x plus 4. Now this is a different u from before. You have to be very careful. Maybe you even want to use a completely different color than before. In fact, I'm going to do that. That would have been a really good idea. So let's go with green. So the integral of x plus 4 to the 5th dx. We're going to say let u equal x plus 4 so that du dx is equal to 1. Actually, the derivative of x is 1. The derivative of 4 is nothing. Multiply both sides by dx, and you get du is equal to dx. And normally we'd have to divide by whatever's next to dx, but it's solved. So dx is equal to du. So remember that the things that we're going to plug in are, we're going to plug u in for x plus 4, and we're going to plug du in for the dx. Again, there could have been something else sitting next to the du, it just didn't happen to be that time. So the integral of x plus 4 to the 5th dx is going to become, that's now u to the 5th, the x plus 4 is the u, and then the dx is du. Well, we can integrate this. The integral of u to the 5th is u to the 6th over 6. Now, yes, there's traditionally a plus c, but we just leave the plus c till the very end for all these integration by parts problems. But we don't want to stick this in u. First of all, this u is different than this u. Probably should have done a different letter to be clear, but at least I used a different color. So we have to go back to what u really is. It's x plus 4. So this is really x plus 4 raised to the 6th over 6. This is our v. V was the integral of x plus 4 to the 5th dx. That's what we just did. So this is our v. So let's write everything down that we have now. We know that u is equal to x plus 2. We know that du for the original problem is equal to dx. We also know that dv is x plus 4 to the 5th dx. And we now know that v is equal to x plus 4 to the 6th over 6. Those are the things we'll plug into uv minus v du. The integral of u dv equals uv minus integral v du. So finally we can say our original integral of x plus 2 times x plus 4 to the 5th dx. That was the u dv. dx is equal to formula uv. Here's the u, here's the v. So x plus 2 times x plus 4 to the 6th over 6. U v. And minus the integral of v du. V is again x plus 4 to the 6th over 6. Du was the dx. I love this problem. I really do. look at this right-hand side. Look at this integral. How much do you hate me right now? Because that integral needs a substitution. We don't have a formula for that. Now, here's the thing. With enough practice, you'll start recognizing forms, and it's not all parentheses raised to an exponent. You just increase the power by 1 and then divide by that same new exponent. It's because of the fact this is just x plus a number or x minus a number. If I put a little 2 right here, it changes. If I put an x squared right here, it changes drastically. So for this last integral, we need to, again, go to the side, and let's use, how about purple this time? So the integral of x plus 4 to the 6th over 6 dx. You're going to say, no surprise, let u be x plus 4, so that du over dx is equal to 1. Multiply both sides by dx, and you get du is equal to dx, a coincidence. So the integral becomes that's weird. All right, the x plus 4 is now a u, so that's u to the 6th over 6. The dx is now a du. We can just bring the 6 out in front if we like. Again, you don't have to. The integral of u to the 6th du with a 1/6 in front. You can leave the 6 in the bottom and just know it doesn't affect you. Then you can straight up power rule this. That's u to the 7th over 7. So that's 1 over 6 times u to the 7th over 7. But now we have to go back to what we just called this u, which was x plus 4. So that's the 6 times the 7 in the bottom will make a 42. So x plus 4 raised to the 7th over 42. That is this integral right here. There's a minus in front of it, so be careful, don't forget that. Again, this bit right here is what we just did in purple, and we got this. And of course, there would be a plus c to the side because this will be the final integral. Okay, so our original integral which was x plus 2 times x plus 4 to the 6th over 6 minus that integral of x plus 4 to the 6th over 6 dx is going to become x plus 2 times x plus 4 to the 6th all over 6. You can write that as one big fraction. So this bit right here is what I just wrote. That's this. Then minus, and we just got our integral. It's x plus 4 to the 7th over 42, and now we have our plus c. There's not really a lot that we can do to this necessarily. So I really do expect some people to stop here. But the problem is, if you actually go through and clean this up, if you take a GCF out, this does become much prettier. This does become much nicer. There is a GCF of x plus 4 to the 6th. That is in both terms. It's in this one and it's in this one. There's 7 here. We can only take 6 of them though, because the first one's got 6. So we're going to factor that out. So the original problem becomes, we're just factoring that out. We're taking x plus 4 to the 6th away. So x plus 4 raised to the 6th. And some people will take a fraction out as well. I'm gonna pause on that idea though. And because of the extra parentheses, I'm gonna open up a bracket. It's probably a better idea. From the first one, we're left with x plus 2 over 6. Whether you keep that in parentheses or not is up to you. Then minus x plus 4 over 42. Now, the minus in the fraction, that minus is supposed to be distributed to that, so maybe a parentheses is a better idea for this one. That's up to you. And then your plus c. Well, you can distribute your negative and then you can get an LCD from there. So this is going to become x plus 4 raised to the 6 times. Let me just go ahead and separate the fractions as well. So x over 6 plus 2 over 6 minus x over 42 plus 4 over 42. And the plus c to the side. Sorry, it's kind of squished in there. Well, you might say, oh, well, 2 6 reduces to a third, 4 over 42 reduces to 2 21st. That's fine. But let's just get an LCD across all of these for now. Let's just bump all these up to a 42. Admittedly, you don't have to. There is another way to do it, but reducing these is not a good idea because you'll be combining like terms. So you want to get an LCD, which for the x's is 42. For the x's, for the constants, admittedly, it's 21. But let's just go with 42. So LCD of 42. So this becomes x plus 4 raised to the 6th bracket. So LCD, 6 goes into 42 7 times x is 7x. That's 7x over 42 plus 6 goes into 42 7 times 2 is 14, so that's 14 over 42 minus, the others already have it, x over 42 plus 4 over 42, bracket, then your plus c. Combine like terms, the parentheses at the front stays the same, x plus 4 to the 6th, bracket. 7x minus x is 6x. So that's 6x over 42. And then maybe minus, maybe plus. 14 plus 4 is 18, so plus 18 over 42. Then your plus c. Let's go ahead and just write that as one fraction and reduce as much as possible. If you do, you'll get 21. So 3x over 21, and then 9 over 21. X plus 6 to the 6th bracket. So again, what I'm trying to say here is 6x plus 18 all over the 42, and then reduce as much as possible. C. Final answer coming up, x plus 6. X plus 4, I gotta fix that. X plus 4, I'm going too fast. Oops, draw. X plus 4 to the 6th, bracket, which could really be a parentheses now. And 2 goes in all of those, so that's a 3x. I know I made an error somewhere, didn't I? This is not a number I'm looking for. I messed up my distribution. I pointed it out and then I did it really myself. This minus was supposed to be distributed to the x and the 4. So this is supposed to be a minus, 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 which makes this number change. I'm going to give you a second to catch those errors. To fix those errors, but everything that I just, again, this minus is supposed to be distributed, so that this 4 should be a minus, minus, and that makes that 18 actually a 10, not a plus. It just makes the 18 different when you combine them. So follow me carefully. Let's erase. That plus and that plus should be a minus. This 18 should be a 10. So again, minus 4, so that stays a minus 4. Then 14 minus 4 is 10. 10 and 42 reduce to 5 and 21 when you reduce them. So that's plus 5 over 21. And of course your plus c. One of the hardest problems we've done. There's about 10 problems in this whole course that I'd say are the most difficult, and this is one of those top 10. Because you had to integrate by parts. To complete that, you had to integrate by substitution, and to complete that, you had to integrate by substitution. This is not a fun problem, but this is a realistic problem. This is something that somebody in economics or finance or science could just come across in their analysis, maybe. Because maybe their supply curve is this really odd, interesting polynomial product. Or maybe this is used to approximate a virus's growth in population over time. It's not quite exponential because it is a polynomial, but we can use polynomials to approximate exponentials under a short-term time length. Lots of colors, lots of issues, lots of work involved. Let me tell you, this is not a fun problem. This is not an easy problem. This is a challenging problem. I used to always put a problem like this on the final because of its ultimate importance. I don't know that I'd go this deep in it, but please understand that on the final exam, you could see a problem that you have to integrate by parts and then do a substitution once, maybe. I don't know about twice, and if I did it twice, it would be just like this problem. I can guarantee that. But for most of the problems, it's just a substitution or just integration by parts. But again, point of this, when you do integration by parts, maybe you gotta do substitution as well. When you do an integration by substitution, there's actually ways to integrate by parts from there, but it's just weird and wacky and we don't do that. When you integrate by parts, maybe you have to integrate by parts again. There are plenty of problems out there like that. In particular, just kind of a special memo. If you wanted to do the integral of x squared e to the x dx, now earlier we did x e to the x. And that was last class's problem. The integral of x e to the x, we integrated by parts one time and we got the answer. This problem in particular requires integration by parts twice. When you get to your uv minus integral v du, that integral v du part is going to end up being, no joke, there's another constant or a sign in there somewhere, but no joke, it's x e to the x. So you end up having to do it twice. Now what you could do is you could say, well, I already did that problem earlier and I know that the integral is this thing right here. So let me just go ahead and bar that information. And on a test, that's exactly what I would expect you to do to save yourself some time. So point being, this could be a theoretical test question that involves two integration by parts. In order to do that though, what I would do on the test is I would make x e to the x a problem before it, and then later you see this one and you can just borrow a previous answer. And that would be perfectly fine. So you don't have to reinvent a wheel for part of a problem. That's what mathematicians like to do. Borrow information. Okay, so those were all indefinite integrals. We've also seen definite integrals, so what do? Definite integrals needing integration parts. Do the evaluations on the uv part as well as the integral of v du. So when you're doing a definite integral, the only thing that changes is you're not just going to plug in your upper and lower limits to the very last part you integrate, because remember that when you get that uv, you actually integrated to get the uv. It was part of the integrating dv bit. So because you've integrated to get the uv, you have to evaluate the upper and lower limits there as well. So the formula just changes very minorly, and it changes to this. The integral from a to b of u dv is equal to uv evaluated between a and b, so you plug in the b number, then subtract plugging in the a number, minus the integral from a to b of v du. So you'd have to integrate this part and then plug in the upper and lower limits. Now what's funny is there's a minus in front of this. So plugging in the upper limit actually ends up getting subtracted ultimately when you see the math happen. And then plugging in the lower limit, because there'll be a minus for that, and this minus they cancel and you end up adding it. It's kind of weird. Don't focus on that aspect. Focus on the fact that there's a negative that has to be distributed, that your teacher almost goofed up on in a previous problem, but paid attention and caught it. We're only going to do one of these examples. So let's do the integral from 0 to 4. And again, I say you have to memorize this, but there's really not much variation in what you already memorized. The u, dv, uv, v, du pattern is the exact same. It's just plug in upper and lower limits. I don't really think I need to call that a formula in my opinion. So let's go back to one that we dealt with, well, last class, one that I just referenced. The integral of x e to the x dx. Now I know I just said there's no real need to reinvent the wheel, but we did do this last class, so let's reinvent the wheel. And it is, there's a little bit of difference here with the upper and lower limits, so I think it's just a good idea to practice. So we know that regular substitution will fail because these things aren't a power off of each other, so we got to go to this integration by parts. So we'll say let u be the simpler part, which is x, which makes its derivative 1. Multiplying both sides by dx gives us du equals dx. Then dv is going to be the rest, so dv is equal to e to the x dx. We integrate both sides. Whatever you do to one side, you do to the other. Integrating dv will always give you v. Integrating e to the x will always give you e to the x. There's no extra coefficient in there, so there's no divided by a number. It's a 1. Dividing by 1 does nothing. And you might say to put a plus c here, but A, we always just wait to the last minute with the formula to do that. B, we're actually doing upper and lower limits. So since we're finding the area between a curve, we don't need a plus c anywhere. No c in this problem. So again, the three things that we need are the u, the v, and the du. Those are the three things we'll be plugging into this formula. So what we can say is the integral from 0 to 4 of x e to the x dx is equal to, now you might think, all right, well, you're doing substitutions, you need to turn these into u's values or whatever, but we never actually write u anywhere. This is just to clean up the problem and plug it in for a formula. That's the difference of substitution versus parts. Substitution, you actually do see the integral with u's, whereas integration by parts, you never do. So uv, I don't write uv, I write x times e to the x. That's the uv, but now plugging that in between 0 and 4. And see, I'm still in my American dollar, so I don't switch those numbers. Minus integral from 0 to 4. V times du, v is e to the x, du is dx. So e to the x dx. Once again, we've gotten a simpler integral, one that we actually know how to integrate, unlike the last problem, where it took us a couple of times to get there. Before we do the evaluations, let's just wait till the last minute to do all of those. Let's do the integration. The integral of e to the x is e to the x. Again, literally saw it right there. So this is x e to the x evaluated between 0 and 4 minus, now I might want a parentheses or a bracket because of the minus part, so minus parentheses. The integral is e to the x evaluated from 0 to 4. And again, you might say you don't need that parentheses, but I have a feeling a lot of people will mess up their signs moving forward if they don't put that parentheses there. Okay, and again, evaluated between 0 and 4. So let's plug in 4 and 0 to the x e to the x. So this is the plugging in of the 4. When I plug in the 4s, I'll do it in red. When I plug in the 0s, I'll do it in blue. So this is 4 times e to the 4 minus 0 e to the 0, then minus, and parentheses because we're plugging in the 4 and the 0 into the e to the x, but this minus is outside of that plugging in. That's why I suggested parentheses might be helpful there. So red, e to the 4, and minus blue, e to the 0. Now remember that anything to the 0 power is 1. But 0 times anything is 0. So this is really 4 e to the 4th minus 0. Let's distribute the negative. So that's a minus e to the 4th plus 1. The e to the 0 is 1. Did not mess up my distribution this time. Minus 0 doesn't really need to be written, so we're just not going to write that second term. And the first and third terms are like. This is like having 4x minus x, because they both have e to the 4th as a factor. So 4 minus, there's a 1 imaginarily there. 4 minus 1 is 3. So this is 3e to the 4th plus 1, and that's our answer. If this was an application, you might want the approximation to that, which is 3e to the 4th. Plug it in on your own calculators. I don't want to have to pull up mine. It takes a couple minutes. Actually, I lied. We're going to be ending class early, a few minutes early anyway, so let's do it. Calculator, calculator, calculator. So that problem was 3e to the 4th, so 3, e with an exponent with a 4, or you can make the exponent yourself. Close the parentheses, then not minus 1, plus 1. And we get 164.79, so let's round to the nearest tenth, so 164.8. Or if you round to the nearest whole, about 165. Again, if this was an application, maybe we were finding the area under a curve. Maybe this right here is our profit curve, our profit rate per day. So how much profit we make each day, and then we can integrate from 0 to 4 days to find how much profit we made in 4 days, or 4 years, whatever the time scale was. So we made 164.8. I don't know, is this in dollars, hundreds of thousands of dollars, millions of dollars? Again, it's not an actual application problem, so there we go. I just wanted to give you a setup, an idea for that. All right, and in fact, I'm gonna call it today. Call it there. I really didn't mean to end class this early, but I don't want to do this next section until next class. I really do like integration by parts to be its own class, essentially. So we went over the proof as well as one example last time, then we spent about 2/3, 3/4 of a class today doing that, hour and a half. So I think that'll be good enough. Remember, this will not be on the test for this weekend, if you want to call it that, this Friday, Saturday, Sunday, Monday option. So we finished 4.6. That homework will be due in a week on the 28th. 4.5 is due on the 23rd. That's Thursday. You will have your review sometime late Wednesday. If I can get it done earlier on Wednesday, I will, but maybe by 5 p.m., maybe 1 p.m. It just depends on when I have an opportunity to get to it. I will not have that opportunity today. I do know that for a fact. So remember, test 3 is only going to cover 4, arguably 5 sections. In the ballpark, 15 to 20 questions like last test. There'll be a review. Review will be very similar to the test. So please complete the reviews. I'm not giving you these reviews for nothing. Remember, the reviews are not graded. The reviews are there just to help you study the test. Remember, this is supposed to be your own work. This is not an open note test. This is supposed to be your own work. The topics on this test are integration, just regular old integration, the formulas. We'll see integration of polynomials, exponentials with a base of e, 1 over x type things that lead to natural logs of absolute values. We'll see things that look at product or quotient or chain rules. So then we have to integrate by substitution or by parts. We'll have area under a curve, which is where we have the upper and lower limits. We'll be doing the area between 2 curves. You'll have area between 2 curves where I might give you the upper and lower bounds, area between 2 curves where I don't give you the bounds and you determine them based on where they cross. Remember the area between 2 curves, you have to do the upper minus the lower, but they can change from endpoint to endpoint. So you might have to break it up into multiple integrals. There's a lot of different things going on with this. So next class, we're going to continue on with material that'll be on the final, but not test 3. I normally do 4 tests for this class, but with this unique setup, it's very hard to rationally give you 4 tests, with the 3rd one being so late in the game. So you're not going to have a test by itself on integration by parts, improper integrals, and multivariable calculus, which is the next things that we'll be covering, one of which we already just covered. So there won't be a test by itself on that. And when I did test by itself, I usually did the substitution integration in that as well as throwing a couple random derivative problems just to keep you on your toes. But again, anything seen in the lectures, in the videos, is open for the final exam. So the final will cover everything that was on the first 3 tests, as well as integration by parts, improper integrals, which we'll go over that next time, and multivariable calculus, mainly just multivariable derivatives. We won't really get into the multivariable integrations. So functions and multivariables, derivatives with multivariables, where you don't have to do implicit differentiation. So it's a different idea. And then maybe that last class we'll go over a few applications that I said we would get around to at the end if we had time. So maybe some marginal analysis, maybe some more profit revenue, marginal revenue being the same as marginal cost, you know, something like that, some economics, some fun stuff. But for now, we're going to call it. So please, please, please get your homeworks done. Get to studying. I need to check the due dates for the homeworks. I think I might already have 4.6 set up. But yeah, if you have any questions, per usual, please email me. Have a good one. We'll see you on Thursday. Take care, everyone.